questions. So this first one, we have a box compressed by a spring, and it's going to be launched, and it's going to have to go over some friction, and then it's going to go up a hill. And this other, I say box, but it's really just this dot here, M2, is going to be released, and when it swings down, it's going to be right here at the exact same time. It's going to be vertical right here at the exact same time this one. So there's going to be a collision. Okay, so find the velocity of box 1 and 2 before the completely inelastic collision. Okay, completely inelastic that means they stick. If it said elastic, that would mean they bounce and we don't lose any energy. And if it's just a regular old inelastic equation, it just bounces and it loses energy. Remember, most things are inelastic. Only in very special cases is it elastic. Thus, in the collision itself, we don't lose any energy. Okay, so to find the velocity of the boxes before the collision, we are going to use energy. M1, this spring has some stored energy, which would be this 1/2 kx squared. It's going to lose some of that energy as it goes over this rough patch. And so the force of friction, which is mu mg, times d is then the work done by friction. So we have the energy of the spring minus the work done by friction, and that's going to be converted to the energy it has up here. Well, it's got mgh, and it's got 1/2 m1 v1 squared. So this equation right here is the equation you'd use to find the velocity of box 1 right when it's at the top of the hill. Okay, as far as the velocity of M2 when it swings down and becomes vertical, it's got mgh at the beginning and it's got 1/2 mv squared at the end. And we know that we've done this geometry a lot of the change in height. Remember, it's all about the change in potential, not the actual height of M2. It's how much height it loses, is that L minus L cosine theta. And that finds you the velocity. Okay, that's going to be important to know how fast these things are moving before they collide. The tension in the string, again, anytime you want to find tension, you're going to draw a free body diagram. The free body diagram here is pretty easy. Tension is up and gravity is down. And we know F equals ma, and in this case, it's moving in a circle as it kind of rotates around. And so we say F equals ma, the force is T minus m2g. It's T is winning because the inward force, remember, if something is moving in a circle, there must exist an inward force. In this case, the inward force is T. There is an outward force, in this case it's down, of m2g. And that inward force causes circular motion. In this case, we're going to rewrite A as v squared over r, where r, the radius of the circular motion, in this case is the same thing as the length of the pendulum. Okay, that allows us to find the tension in the string at that moment because we know the velocity at that moment. How fast is it rotating, meaning omega, and that would be the fastest at the bottom. Then we just use V equals omega r. How fast you're moving is related to how fast you're spinning and how far you are away from the pivot. Again, that's a classic circular motion equation, so we can figure that out. Now we want to find the boxes after the collision. Okay, all we need to do is conserve momentum. Remember, you think of a collision, you're going to think momentum. And this collision doesn't really cause a rotation. They're just two things. And so this is the momentum before the collision, and this is the momentum after the collision. After the collision, since they stick, we can treat them as one mass moving at one velocity. Momentum is a vector, which is why this needs to be a minus sign. M1 is moving to the right, M2 is moving to the left. Afterwards, we can see that we get a positive velocity for V final, which means they are moving to the right afterwards, which also meant that this quantity must have been bigger than this quantity. Thus, when they hit, more momentum goes to the right. All right, now about the heat in the collision. Okay, so we need the energy right before the collision, which is the kinetic energy of the two objects, and then we need the kinetic energy of them afterwards, which is that guy. And it's the difference between those two things. So it's not the original energy at the very beginning with the spring. The heat produced in the collision is simply the energy lost right in the collision. And so we need the energy of the two objects. And again, this is an addition sign because energy is a scalar, even though they're moving in other directions. They both have kinetic energy, and then together they have kinetic energy. And the difference there then is the heat produced. The distance on the ground, this is like classic fake projectile motion. When this thing comes off, they are at that moment right there after the collision, we know how fast they're moving, and they are moving to the right. This is like a ball rolling off a table or something launched horizontally. This is not with V's and or V naught, cosine thetas, and sine thetas. I mean, you could use it, but cosine theta would just be 1 because it's launched horizontally, and the sine theta would be 0 and it would just go away. But this is kind of our classic. We know that the time is like it's dropped, h equals 1/2 gt squared. And then the distance it goes is just vt because we don't, I mean, fine, put in v cosine theta if you want, but it's still just going to turn out to v. And we use the 1.45 because the velocity it's moving after the collision is completely horizontal, and it will stay moving that velocity the entire time. The period of the pendulum, again, this is just a formula that you should know. It's given to you on the AP test. But you don't want to have to look for it. You should know that the period is related to the length of the pendulum, and then, of course, the gravitational pull of whatever planet you happen to be on. The period of the spring is another formula. Again, you should know. The more massive, the longer the period, the tighter the spring, the stiffer the K, the smaller the period. Again, period is the time it takes for one rotation or one total revolution or one cycle, which is in seconds, and same thing up here. Find the initial alpha. Anytime you want to find alpha, you know you need to analyze torques. Torque equals I alpha. The torque, again, draw the force. The force on this thing is gravity. The lever arm is L, and the sine of the angle between them. And we just kind of plug in I for a point particle is mr squared, where r is L, and then we can find alpha. And then you just kind of plug in numbers there. Find the angle of impact. Okay, it's always this triangle, and it's always going to be inverse tangent. We know that we want to find this angle right here. We need to know how fast it's moving horizontally and how fast it's moving vertically. How fast it's moving horizontally is just the 1.45 because that doesn't change during the flight. How fast it's moving vertically, well, it didn't have anything at the beginning, and so it's just like how long was it in the air for times 9.8. That's going to tell you how fast it's moving vertically, and we know it's negative because it's going to be down, and then we do inverse tangent, opposite over adjacent, and then we get an angle, and of course that's below horizontal. Okay. All right, new problem. All right, now we got these two boxes attached to a spring. The spring is compressed. We're going to release the spring, and they're just going to fly out. This is an explosion. I know it doesn't, start a fire or destroy anything, but this is an explosion, and you have to conserve momentum. Okay? Whatever momentum goes to the right, the same momentum has to go to the left because there's no external forces. So P1 equals P2, but P1 is 0. The thing isn't moving. And really what we're saying is the momentum M2V2 to the right has to equal M1V1 to the left. And we know some of these values up here. And so we can figure out how fast V1 has to be moving to the left. Okay, now they tell you this spring is a nonlinear spring, meaning it doesn't follow Hooke's law. It's not linear. It's not F equals negative kx. This is a nonlinear spring. And so since it doesn't follow negative kx, we cannot use 1/2 kx squared for its energy. We have to integrate. Now, you all know how to do the power rule at this point. So we have to integrate that force over distance, and we end up getting, don't worry about the negative sign, that's just the direction. We end up increasing the power by 1 and dividing by the new power, so we get this 1/4 kx to the 4th. That's the energy stored in the spring. And we know how fast the two boxes were moving after the spring was released. So we add them together because energy is a scalar. So this is how much energy the spring produced, which must then equal how much energy it must have stored. And then we can figure out the compression. Okay, when the box is on the ramp, we have the normal force is normal, friction is down the ramp, mg is down, and again, it is moving up the ramp, but there is no force forcing it up the ramp. It just goes up the ramp because that's the direction it was going. As soon as it starts to go up the ramp, it is going to start to slow down because all the forces are going to slow it down. Okay, find the distance on the ramp, it will go. Okay, you can do this with energy if you would like, or you can do it with accelerations. I particularly think energy is always the easiest, but I did do forces here because I think we needed a good review of that. So in the y-hat direction, we have classic n equals mg cosine theta. And then in the x direction, we know both of these forces are down the ramp. So the acceleration is going to be negative. It's going to be slowing you down. mg sine theta is the force of gravity down the ramp, and friction, mu mg cosine theta, is down the ramp. Again, add those together and find the acceleration rate. Then we can come over here and find how far it will go distance-wise, x. And again, this is a minus sign because we know that the box is slowing down to rest at some point, and we can then find d. And if you wanted to find the height then, well, then you could use trig. If you know how far it went up the ramp, you can figure out how high it is on the ramp. All right, find the time it takes. Again, this, I guess there's two different ways. This one is just using classic v equals v naught at. We know the acceleration, we know it stops, and we know how fast it started, so we can figure out how long it would have taken to slow down. Or we can kind of use the position equation to know how far it went up the ramp, how fast it was moving at the beginning, and the acceleration rate, and we can find, again, both of those will give you the same time. Okay, find the normal force acting on box 2 at the top of the loop. Okay, so now we're focusing on the top of the loop-to-loop, and we know at the top of the loop, the normal force and gravity are both down. Okay, so N plus mg equals mv squared over r. And again, we replace a by v squared of r because we're talking about circular motion. We have to figure out the velocity on the top, and again, that uses energy. Okay, so this is the kinetic energy at the bottom of the loop. This is the potential energy at the top of the loop, and this is the kinetic energy at the top of the loop. Right? We conserve energy as it whips around. This gives us the ability to find the velocity at the top. Once we know the velocity at the top, we can go back here and figure out the normal force at the top. Okay? 17 says, well, what's the minimum velocity? It's like, well, the minimum velocity we know is when the normal force goes to 0. Because if you're going just slow enough that you just make it around, the only force making you move in a circle at the top is mg. So you set mg equal to mv squared over r, and then you get what most of you have memorized, that the minimum velocity is the square root of gr. Okay? And does it make it around? Of course it makes it around. We just showed you that the velocity is 11.6. All it needed to be moving was 1.56. So yes, box 2 is for sure going to make it around the loop, because and the normal force is necessary. The normal force is going to be huge. Again, we already knew that the normal force was this big value. So yes, the ramp for sure helps it move in a circle. Okay, so now we're putting the box on the side of the ramp. So now we have actually two different types of things happening here. We have a linear acceleration or a tangential acceleration. It's speeding up, in this case down, and it is moving in a circle. So we know that the circular motion is caused at the right just by the normal force, by the inward force, and then the linear acceleration is caused simply by gravity. And so at that point, it's actually falling at exactly negative 9.8. Again, negative because it's down. All right. Okay, this one threw out some projectile motion. So this is a good review of, okay, what if the ramp, it flew off this ramp? We already know now the distance of the ramp is 1, the acceleration we already knew, and we knew the initial velocity. We can do this guy right here, the v squared equation, to find the velocity at the top of the ramp. That's important. Because that's the velocity we need. Okay, so now we do a whole new projectile motion. We know that this is our projectile motion equation. Y equals y naught plus v naught sine theta t minus 1/2 gt squared. Initial height, again, how did I find the initial height? Well, I used geometry. The distance was 1, and the angle was 30 degrees. And so on a 30, 60, 90 triangle, or you can just figure it out using sine or cosine, well, sine in this case, you can figure out that this must be a half. So when it's right here, we know how fast it's moving, 4.6. We know the height of it is 0.5, and we know that it enters free fall, so we know what gravity is going to do. Okay? So we could just graph this and find the time when it hits the ground. That's the time it takes to hit the ground, and then we can figure out how far it must have gone because we know how fast it was moving horizontally, v naught cosine theta, and then times that t. That will tell you the launch distance. So this one gave you a little old school projectile motion where you have to actually do the angle, where I think the first question was more fake. Okay? Hopefully this video helps you kind of walk through all of those concepts.